Right after a couple weeks of listening to me talk in class and write furiously on the board, you're ready to be back to this. So we're going to baby step back into it. You should have a notes packet. We're just going to fill in the notes, and we'll just jump right in. Our topic tonight is talking about liquids, solids, and intermolecular forces, which kind of wraps up this whole unit on bonding. So a couple things are just how are gases, liquids, and solids different? Now you probably had something like this in whatever chemistry you had previously, but shapes of gases, liquids, and solids. What kind of shape does a gas have? And really it's going to be one or the other, definite or indefinite. And a gas has, for sure, indefinite shape. So we're going to put in def. Liquids, do they have a definite shape or indefinite shape? Again, indefinite. Whatever container we put our liquid in, that is the shape it has. Right? And then solids, they have a definite shape. Right? Doesn't matter if it's in a beaker, graduated cylinder, if it's a marble, it is round. Okay? Volumes. Gases have indefinite volumes. And they take up whatever space they're in. Liquids have definite volumes. If we pour out 10 milliliters in a graduated cylinder and pour that into a beaker, it's still 10 milliliters. It looks different because it takes the shape of its container, but it's still 10 milliliters. And then lastly, solids have definite shape or definite volume as well. How do things diffuse? And diffusion has to do with how things spread through another medium. Okay, so gases diffuse really, really well, or you might say gases diffuse rapidly. And liquids, not quite as rapidly as gases, but if we put food coloring in some water, what would happen? Eventually that water, if we put green food coloring, would turn completely green. But as you put it in there, you can see where the green is. It's really going to take forever unless you stir it, but once you stir it and kind of get it agitated, it spreads quickly. But we might say that liquids really diffuse fairly slowly if we just leave them to diffuse on their own. And then solids do not diffuse, because there's really not a whole lot of movement when it comes to solids. Next thing, asked me to do this demo. It's one of my favorite demos that I do all year. It's not blowing up anything, but it's certainly my favorite non-flammable demo. So anyways, remind me to do this tomorrow. But fluids, obviously liquids flow. So yes, liquids flow. Solids, they do not flow. If you have something like magma, I don't know if we're talking about volcanoes, what is magma? I would say it's liquefied rock, so it's a liquid. And then gases, they flow as well. We don't think of gases as flowing, but they flow. And we'll look at that tomorrow. Alright, so the next big thing we're looking at is intermolecular forces. Why is my screen not? There we go. Intermolecular forces are due to electrostatic attractions between positive and negative charges. So the first thing we're going to look at is ion dipole. And based on its definition, it is between an ion and something that has a dipole. What is a dipole? A dipole is any time where we have two basically covalent compounds, or two nonmetals that are in a covalent compound. So two nonmetals with varied En. And En is just going to be electronegativities. Electronegativity is the ability of one atom to attract the electrons of another atom. Alright, the most electronegative atom is fluorine, and the least electronegative is francium. So it's high in the top. If I'm looking at you, it's high up here in fluorine, top right. It's very low down on francium, bottom left. And then noble gases have no electronegativity. They don't want to attract electrons. They're stable the way they are. So an example of this might be sodium ion. If we had some sodium chloride maybe in water, and we were to mix some carbon monoxide. Carbon monoxide is triple bonded, got two lone pairs of electrons. But if we look at electronegativities, the oxygen side is very negative. This little symbol right here, sigma, Greek symbol, sigma, just means partially negative, where our carbon side is partially positive. Okay, electrons tend to gather on the oxygen side. If the electrons gather on the oxygen side, it means they're leaving the carbon side, so the carbon becomes positive, the oxygen becomes negative. So if we had some sodium ions, they would be attracted to the oxygen side. Because it's not really a bond, we might just do dashes between them, just to show there's an attraction between this sodium and this oxygen. It's not really a bond, but there's a really strong attraction there. As far as strength goes, we might say it's approximately 10 to 50 kilojoules per mole. And that's a fairly decent strength for an intermolecular force. And again, those are between molecules. Our next one that we're going to look at, or really the next three, so scroll this down a little bit. All three of these, 2, 3, and 4, fall under van der Waals forces. In terms of strength, hydrogen bonding is by far the strongest, and the weakest is London forces. All right, and somewhere in between those is dipole-dipole. But hydrogen bonding we define as the hydrogen on one molecule So hydrogen on one molecule, or molecules, that doesn't make any sense. Hydrogen on one molecule is attracted to an unshared electron pair on an N, O, or F. Okay? So the hydrogen on one molecule is attracted to an unshared electron pair on an N, O, or an F. What are N, O, and F? They have the highest electronegativity. So generally speaking, these things are always have extra electrons on them, which means they're partially negatively charged. And the hydrogen on the other molecule, this hydrogen is attached to something that has an N, O, or F. So if we were just to draw a couple of waters are our best example of this. We've got O, and our water's bent, and we have a couple of electron pairs here, and we have another hydrogen, or we have another water over here. Okay? On our O, we have a really strong partial negative. On our H's side, we have a really strong partial positive. Okay, so the hydrogen on this water, okay, because all these molecules are the same, so this H, which is attracted to an O, it is partially positive as well, because this O is attracting so much of the electron density. So what happens is we get a attraction between this H and the O right here. Okay, and that is the hydrogen bond. It's not really a true bond, but it's just a really strong attraction between two molecules. Again, the range is about the same as ion dipole. It's about 10 to 40 kilojoules per mole. And we're going to see here in a second that that's quite strong. Let's see, dipole-dipole is just what it sounds like. Between two polar molecules. Okay, dipoles only occur on polar molecules. So again, a dipole between two polar molecules. And let's go back to our last example, carbon monoxide. So again, if I were to draw a CO molecule and another CO molecule, looked at this already, but big time partial positive, quite partial negative, another partial negative, another partial positive. So if these molecules get anywhere close to each other, there is going to be a strong attraction between the O on one molecule and the C on the other molecule. Okay, so again, we have attractions between molecules, which is an intermolecular force. And again, our range on these, range isn't too important as long as you know just kind of the scale, is 3, that's a terrible 3 to 4 kilojoules per mole. So as you can see, dipole-dipole are about 10 times as weak as our hydrogen bondings. Okay? And then lastly is London dispersion forces. And London dispersion forces are probably the hardest to explain. The main thing to know about London dispersion forces is everybody has them. Okay? So where specifically hydrogen bonding, It's only things that have H's with N's, H's with O's, H's with F's. Dipole-dipole is any polar molecule, which goes back to why we did bonding this last week. And then London dispersion is all molecules. I already have my right color, so this is all molecules. Alright, how do we know London dispersion forces occur? It's possible that we can take things like noble gases, such as argon, which is a gas. If we cool it enough, it turns into a liquid. If we keep on cooling it, we can turn it into a solid. But making liquid argon is not that difficult. But why can it become a liquid? Again, if we could kind of go up to this last thing, which was right up here. Liquids and solids have lower temperature. Lower temperature equals lower kinetic energy, which means the molecules are closer together. They're moving less quickly, which means if they're closer together, they have the chance to be more sticky with each other. If they stick to each other, they turn into liquids. If they stick to each other and stop moving, then we have a solid. Okay? So kind of think of intermolecular forces as stickiness. So if we go back to London forces, because we can get noble gases, okay, which have no dipoles, because we can make them liquids by slowing them down and freezing them, they must have some sort of attraction for each other. So if we take something like, we've already talked about argon, so here's argon. Electrons are scattered evenly, okay, if we look at Lewis dot structures. But realistically, is that what electrons look like? No. This electron pair up here doesn't stay on top. This electron pair doesn't stay over to the right. These are 8 electrons moving constantly around our nucleus. Okay? So if for one instant in time, okay, in London dispersion forces, if you can just think of instantaneous or super temporary, instantaneous or temporary, and oftentimes these are called temporary dipoles, because they are polar molecules which exist and then they change. So at one point in time, okay, and these electrons are moving, so these points in time last for just moments. But let's say all of our electrons happen to be on the right side of our argon. At that moment in time, this side of our argon is very much partially negative. At that same moment in time, what's this side of our argon? It's very much partially positive. So if these molecules are moving slowly because we've lowered the temperature, when this side becomes partially positive, what's going to happen to the electrons in this argon? They are going to move to the right side of this argon, okay, making this argon partially negative. And likewise, if that starts negative because the electrons have moved to the right side, then the left side is going to be partially positive. So for that moment in time, is there an attraction between positive and negative? Sure. Okay, we have a temporary dipole. Where are the electrons the next moment? They're somewhere else. But if these molecules are close together, these electrons are causing an attraction between molecules. Okay. Alright, the range for London dispersion forces are even smaller, probably in the scale of 1 to 2 kilojoules per mole. And there is a term you need to be familiar with that has to do with London dispersion forces. And that term is polarizability. It is another great word to use on the AP test. And polarizability essentially is the ability for something that is essentially not dipole, so not polar, to become polar. Alright, so polarizability, kind of the trend that you need to be aware of is that the larger the size, so again, if we think in terms of periodic trends, as we go down the periodic table, our atoms are getting larger. So the larger the size equals stronger IMFs. Alright, so a practical thing of this would be if we compare helium to neon to, what's next, argon. Okay, so as we go down, helium has 2 electrons, neon has 8 electrons, argon has 18 electrons. So as we go down the periodic table, each of these molecules has more and more electrons, which means it has a greater chance that the electrons can be at one side. If the electrons are more on one side, that is a much stronger dipole. Okay? So if they have stronger intermolecular forces, What happens to boiling points and melting points? Are they going to go up or down? So if they are really, really sticky with themselves, if the strength is strong between them, it's going to take a higher temperature to boil these things or a lower temperature. And what's going to be true about it? It's going to take a higher temperature to boil them. Okay, so stuff like argon might have a high boiling point. Something like neon, a little bit lower boiling points, or we'll just say helium has a really low boiling point. So, helium might be, I don't know, a liquid at, well, let's start with argon. Argon might be a liquid at 100 degrees Celsius. But at 200, it is now a gas because it has a really high boiling point. Neon, though, because it has a lower boiling point, would be a gas at 100 degrees. Okay? Or helium, because it has a really low boiling point, it's going to be a gas at 10 degrees. But strength of intermolecular forces determines what boiling points are going to be. So helium is a gas at pretty cold temperatures, where neon, we can freeze it at a higher temperature. Argon, we can freeze that at an even higher temperature. Okay? A little bit of just practice with some examples of intermolecular forces. Again, type strength of ion mass responsible for physical characteristics such as melting points, boiling points, and we're going to look at a couple on the next slide as well. So, some examples. Lewis structure for hydrochloric acid, HCl. And we have kind of electrons like that. And then basically, does this have London forces? Yes, everybody has London forces. Okay. Does this have dipole-dipole? Well, is this molecule polar? Okay, so if we look at its electronegativities, we will see that it is polar. So yes, this has dipole-dipole. Does this have hydrogen bonding? Oh, look, it has a hydrogen. Is it hydrogen bonding? No, because what does that hydrogen have to be attached to? An N, an O, or an F. Chlorine has fairly high electronegativity, but not strong enough to be categorized as a hydrogen bond. So it does not. If we look at C2H6, I'm kind of giving you a hint on how to write this, but anyways, it is going to look essentially like this, with H's everywhere. Over Christmas, you get to learn how to name this. This is ethane. But does this have London forces? You betcha. Okay, everybody has London forces. Is this a polar molecule? If we kind of think in terms of tetrahedral, all of our H's are pulling equally. We have two C's kind of connected to each other. So really, everybody's pulling equally in all directions. So no, this is not polar. And then if it's not polar, there's no way it can have hydrogen bonding. CH3NH2. Right, so this one's going to look more like this. We've got C's attached to 3 H's, attached to an N, which is attached to 2 H's. And we have some lone pairs of electrons here. So, is this London? Yes. Alright, if we look at this molecule, is it symmetrical? It is not, so it must be polar. And then does it have hydrogen bonding? Yes, if we were to draw another molecule of this, we could have H, here's our N, our C, and then our 3 H's. Where hydrogen bonding would occur would be between an H on one molecule and the lone electron pair on an N on the same molecule. Okay? So yes, that does have hydrogen bonding. We have all 3. And then lastly, just one last example, krypton. Alright? What does it look like? I just do our 8 pairs of electrons, and krypton is a Kr, not just K, Mr. Burkett. Does it have London forces? Yes. Is it polar? Definitely not. And there's no H's, so there's no way it can have hydrogen bonding. Okay? The very last thing, properties of liquids. Many depend on IMFs. So viscosity. Viscosity is defined as the resistance to flow. Alright, resistance to flow. If something does not flow very easily and it's a liquid, it is known as being viscous. Alright, stuff that's viscous would be honey, What else? Molasses. Probably oil as compared to water would be viscous. But resistance to flow. And resistance to flow, if we have strong IMFs, so strong IMFs equal high viscosity. Alright, and once you look at stuff like honey, it is just a big hydrocarbon, just a big chain of carbons with a bunch of hydrogens on that. If we look at how many electrons are in one of those chains, not only is it long and it can kind of wrap around itself, but because of all the electrons, it has really, really, really strong London dispersion forces. If we look at surface tension is going to be the cohesion or adhesion between molecules on a surface. Alright, so again, if we think of water, so you've probably seen movies with like water striders that walk across water. Why can they walk across water, but if they were to try to walk across an alcohol or across acetone, which is fingernail polish remover, can they not walk across those? Same thing is viscosity. If we have strong intermolecular forces, we have strong surface tension. Or we should call it ST. So those molecules on the surface, because they're attracted to each other so strong, they link up, they're sticky with each other, and then you have things that can walk on the surface. Again, I can try to do this in class tomorrow, but we can put a paper clip on water and just float it on water if you put it on there very, very gently. Okay? And how does the paper clip not sink? Because the surface tension, as long as that paper clip doesn't break the surface tension, the water is so sticky with itself that it keeps the paper clip up. Our last thing is vapor pressure. Alright, and vapor pressure has to do with liquid molecules with average kinetic, or with greater average kinetic energy. Liquid molecules with greater average kinetic energy can escape a liquid and become a gas. So if we were to draw a flask and put a stopper on it, okay, and here's kind of our liquid level right here. If we have really strong intermolecular forces, what's true about the surface tension of this surface? So we have all these molecules in the bottom. Alright, so if we have strong intermolecular forces, so now we're thinking of not really stuff being on top and sinking, but what about these molecules that are speeding around on the bottom? Can they break through this surface tension from the bottom to turn into a gas very easily? And the answer is no. So strong intermolecular forces, there's strong surface tension. So we have very few molecules that turn into gases. Okay? And then vapor pressure then is if we have this thing capped, a certain amount of pressure builds up in the top of our flask. Okay? And certain of these molecules that have enough energy, that are moving faster, become gases. And if the gases are moving fast enough, they might break through the surface tension and become liquid again. But if this surface tension is strong, because our intermolecular forces are strong, we have very few vapor molecules. So strong intermolecular forces equal low vapor pressure. And the converse is also true. Weak intermolecular forces. Who's going to break through the strength of these if it's really weak? There's lots of molecules that become gases, so we have a lot of molecules up here, which means if we have a bunch of molecules, our pressure goes up. Okay? And that is it on intermolecular forces. We'll have a short podcast on types of solids tomorrow, and that is it.